Hello everyone, good evening. My name is Vedant Singh, and in today's recitation video, we are going to learn about data pre-processing techniques. If you've seen the previous recitation videos, you all know that we spoke about dataset class and data loader class and how to develop them. So post that comes the data pre-processing once you guys have already made your dataset class and a data loader class. So data preprocessing is actually a very important and an essential step in your machine learning or a deep learning pipeline. What this step actually does is that it ensures that the most important, essential, and relevant information is passed to the model. So say we have like a speech classification task or any task like that, we want the model to only be presented with the most relevant information so that it is able to make it's able to predict the correct class, or it's able to predict the next time step value in the most correct or most efficient manner. So in today's video, we're going to learn about how do we pre-process audio data sets in such a way that when the model has to learn for any given tasks, it is it has the most essential characteristics. Now our raw audio waveform is in the form of sound signals. We've always seen any audio waveform usually in this manner, where basically we have our variation in amplitude against your timestamp, and we see how with each utterance or with different transcripts or phoneme IDs, we basically see the variation in amplitude. So usually our audio data set is in the form of your sound signal that is mapped to your phoneme ID or text. So this audio waveform is essentially meaning like if someone has said, eat your raisins outdoors on the porch steps. This is how the audio waveform is going to look like. You see that each audio waveform is mapped to its particular texts or a transcript, and that has its own phoneme IDs. Okay. Now we cannot directly insert this data set into the model for several reasons. One of the most important reasons being that it is very high dimensional. Like it has so many irrelevant information about the sound signal that the model does not need to know. So for an example, say if we think of T as the total number of samples and we just want a 2-second utterance. A 2-second utterance is essentially going to be of the form of 32,000 channels, like that much information. It is not needed for the model to know so much for like say a sound classification task. We want to map this data into we want to recognize the most important features in this data set. So we go through data pre-processing steps. Second reason why we do this is because we want the model to be robust. While we speak, there will be different utterance types, different talking styles, accents, etc., etc. So we want the model to be more robust so that if suppose even if the data set has some sort of like information missing or something, it is able to predict it very well. So we artificially kind of expand the data set. Thus, these are the reasons why we need data pre-processing as for the audio data set. Now, how do we do that is something called as we extract features by converting a raw audio waveform into something called as MFCC, Mel Frequency Cepstral Coefficient. Okay, now what MFCC basically does is that it converts your amplitude or your raw audio waveform into in the frequency domain. Now, this is done by also mapping it from a very high dimensional into a lower dimensions so that the most important frequencies are highlighted, the most important amplitudes are highlighted. Let me tell you all that you all are not required to do this in your homeworks, like converting from raw audio waveform into MFCC, because we already give you guys the information or your data set in the form of MFCCs. But it is very important for you all to know that the data set that you are dealing with, the MFCCs, are what do they actually represent? Okay, so in order to understand that, let's go through the code. First, we load the data by we first import certain important libraries, which is usually used in Python to load any audio data set. We make use of this very rich data set bank, which has your audio data set mapped to its transcript or its phoneme ID, which we saw above. Once we've loaded a couple of data points, we can now see that how the data is going to look like.
Measure of truth, though the word exactly might seem an overstatement.
You guys saw this is a normal audio, uh, like an or your normal MP3, MP4 or something, which we usually have seen across, in many places. Now, if we plot this, we see that it is a data set of length 16 seconds, and the shape is almost it's it's about 2,063,600 channel. That is way too much for a model to process. So what we're going to do is we're going to convert this into a MEL spectrogram. We take the raw audio and we convert it into a MEL spectrogram so that it analyzes the amplitudes and converts it into a frequency domain. The math behind it is a little complicated, but the main idea feature who have learned math in their undergrad, well, or the fast Fourier transform. This is what is essentially done, okay, to convert it from your amplitude versus time domain into a frequency time domain. This is what how a MEL spectrogram looks like. From this MEL spectrogram, what we essentially want are the MEL frequency cepstral coefficients, the MFCCs, what we spoke about. Now, the most important parameter in this is the number of coefficients that we want. Now, this is not something that is expected of y'all, or is this not a hyperparameter that y'all need to tune? We give you this information, we give you the MFCCs in the part of the data set itself. So, but this is something that y'all should know that if this is the shape of your data set, this is not your raw audio waveform, this is your MFCC data set. Okay. Now, post once you have got this is something what we do a cepstral normalization. Now, this is a very standard technique. We do not want that any part of your data set or to be influencing much greater than any other part of the data set, right? We don't want that, say, a frequency at one part is so large that it influenced the data set or created a bias. So what we do is that we have a standardization technique where we take the MFCC to the mean of 0 and a standard deviation of 1. This essentially, there are several benefits like mentioned, reduction of noise impact. The raw audio waveform, if it has noise, it completely reduces the noise impact of that. There's better robustness across environments. The feature discriminability is enhanced. After applying this norm, now we apply this normalization in the following way. This is our normalized MFCCs. This is expected of y'all, like after you guys get your MFCC data set, normalization and data augmentation is something that is expected in several homeworks from y'all. Now, how do we augment these MFCC data sets? There are two methods to do it. By time, one is time masking and the other is frequency masking. Time masking essentially is a concept where in that particular time frame or in that particular data set, we cover a small patch from the model so that the model becomes more robust and the model knows how to handle incomplete information, or the model knows how to handle information or predict data set in that particular patch. Okay. So this is something that we do so that the model does not overfit to the particular data set that we've provided. Now, time masking is done with two most important arguments. One is your time masking parameter and the other is your P. Time masking parameters is like determining what is the maximum possible length of the mask. You see, this is how our MFCC looked like, where this is your MFCC and this is your time, and we have masked a certain patch of time. The maximum length parameter length we've set is 100. P is equal to 0.2, which is the proportion of time steps that can be masked. It has to be between 0 and 1. We do a very similar technique in frequency masking, where we determine the frequency masking parameter and we mask that patch of the frequency MFCC from the model and expect it to learn that patch data as well. Now, this is on a particular data point that we do. What if you want to do it on a mini batch or something? So first we load all the audio waveforms, we convert it into MFCC, we make all the MFCC into the same length, so that's how we do data preprocessing. That's how we do data preprocessing. We pad it so that they are all of the same length, all the MFCC, that they are not of different lengths. And then we plot it. See, this is how our first MFCC data point looks like. This is how our second data point looks like. Now, if we want to do basically time masking on both of these MFCCs, this is how we are particularly going to do that. Like we mentioned that we want to mention about our time masking parameter and our P. IID masks are basically, like we mentioned over here, they are whether you want to apply different masks to the different channels or you want, or batches, or you want to apply the same mask. So if it is true, it basically means that we want to apply different masks to different channels. We don't want the model to just learn that mask itself. We want that it should be able to develop robustness or develop an understanding of the data set where there are where the masks are at different time steps. So we do that. And this is how we basically pre-process our data by masking it at different time steps. We can do this similarly for our frequency time steps as well. Both our MFCCs have frequency masking at different frequency wavelengths. This is all for audio data pre-processing. Thank you very much.